Hi, Matthew. We are on our last lesson of the school year, which is crazy. So we are going to do 7.1D, linear and nonlinear patterns, and then we're just going to do a little snippet of 7.1E. And remember, we are only doing crucial lessons to help prepare you for next year in high school, so make sure that you're taking good notes and paying attention throughout this video and pausing when you need. Okay, so here we go. Complete Foods, a local grocery store, has hired 2 different companies to design a display for food items that are on sale each week. They currently have a display that is 6 boxes wide. So this is their display right now. They would like the center part of the display to be taller than the outside pieces of the display to showcase their mega deal of the week. The following are designs that 2 different companies submitted to Complete Foods using the current display as their starting point. So we're just going to focus on design team 1 at first. The current display is just 6 boxes. The next stage would be 2 boxes added to those 6 boxes. And then stage 3 would be, again, 2 boxes added on top of that. So it says, draw stage 4 of this design, explain your process. So the first thing that I see is these 6 boxes. This is constant in every single stage. So I'm going to first draw those 6 boxes. So let's try and make this as even as possible. And then the next thing I see is that this has 2 boxes here, and then each time we're adding 2 boxes. So if I'm going to draw stage 4, stage 3 is the same as stage 2 with 2 more. So I'm going to first draw stage 3, and then I'm going to add those 2 boxes. So this is what I added this time. Can the relationship between stage number and number of boxes in a stage in this pattern be modeled by a linear function? Create a table, graph, and equation to support your answer. So it's asking this, is this going to be a linear function? And the evidence is going to be a table, graph, and an equation to support our answer. So let's first do the table, and we're just going to start with stage 1, 2, 3, 4, and 5. So the number of boxes in stage 1 is 6. Then we added 2 to that. So the number of boxes in stage 2, if we're going to go back and count, we have 6 plus 2, so that's going to be 8. Stage 3 is going to be 10, and stage 4 is going to be 12. So stage 2 is 8, stage 3 is 10, stage 4 is 12, and then if we were to go and draw stage 5, we would have 14 boxes. It's going to ask, is this relation a function based on the table of values? So if I'm looking at the table of values, I'm going to first look at my inputs. Remember, this is the input, and then this is my output. And yes, because every single input corresponds to one output. So yes, each input has only one output. Is the relation linear based on the table of values? Well, in order to find if something is linear, we in the past have said, okay, if this is just going up by 1, 2, 3, 4, 5, we can say, how do I get from stage 1 to stage 2? Right here, I'm adding plus 2. How do I get from stage 2 to stage 3? Plus 2. And if we look, we do this every single time. So what we call this plus 2 is called the first difference, because it's the difference between the y values, or the difference between the output. So if it's asking if it's linear, I'm going to say yes, Oops, go away. Yes, the difference between the number of boxes is constant. And I'm going to say is constant as the stage number increases by 1. The stage number increases by 1. I really ran out of room here. Okay, for my graph, I'll just use a different color so that we know that this is for all the graph. So if I'm in a graph, I go over to stage 1 and up to my number of boxes. It already has us labeled the stage number and the number of boxes as 1, 6, then 2, 8, 3, 10, 4, 12, and then it would be 5, 14. And this is actually going to be a discrete graph because these are not going to be connected. We just jump from stage 1 to stage 2, stage 3, stage 4. We don't have any in-between stages. Then it asks, is this relation a function based on the graph? Well, we can, if we do the vertical line test, the vertical line test says that if I draw a vertical line anywhere on this graph, it should only pass through 1 point. So I could draw a vertical line anywhere on this graph and it would only pass through 1 point. So I'm kind of drawing dots of like multiple vertical lines here, but anywhere that I had a line, it would only pass through 1 point. So I'm going to say yes. And this is a line, but it is not a vertical line. If my graph actually looked like this up and down vertical line right here, then it would not be a function. And then this question hidden down here says, is the relation linear based on the graph? And yes, we're going to say it is linear because the points fall on a line. So right here, yes. The points fall on a line. And then finally, my equation here, we're going to look at what our slope is. So rise over run, I have to go up 2 for every 1 I go over. Our slope is actually the same as our first difference here. So our slope of our equation is 2x, x is our stage number. So our stage number, I have to multiply my stage number times 2. So 1 times 2 would be 2. And then in order to get to 6, I have to add 4. So let's double check. Let's just try it for stage 3. If I multiply my stage number 3, 2 times 3 is 6. And then if I add 4, I get to 10. So my equation works. Another way is that we know that this right here represents the y-intercept. So if I were to go backwards down 2 and over 1, I would get to 4. My y-intercept would be 4. And it says, is this relation a function based on the equation? Yes, this would be a function because, and this would be a linear function because our equation is in y equals mx plus b form. And because it is not vertical. So next question here is just design team 2. So the current display stage is those 6 boxes right here. And then for stage 2, I have my 1, 2, 3, 4, 5, 6. Oh, but then I add 1 here and I add 3 here. Okay, so for stage 3, let's see, I have 1, 2, 3, 4, 5, 6. But then I added another one because I added 1 to stage 2. So I added another 1 here. And then I also added 4 here. So for stage 4 of this, I would have, let's draw first on the bottom. So for stage 2, I added one here, and for stage 3, I added one here. So in stage 3, I have 1, 2, 3, 4, 5, 6, 7, 8. So for stage 4, I'm going to have 9. And then for stage 2, I added 3 in the middle. And then for stage 4, I added 2 rows of 4. So for stage 5, I'm going to add 2 rows of 5. So do 1, 2, 3. I'm sorry, 3 rows of 5. So there's 5 there. There's another 5 there. And there's another 5 there. Okay, so let's double check. I added 2 rows of 4 here, I added 1 row of 3 here, and I'm added 3 rows of 5 here. Can the relationship between stage number and number of boxes in a stage in this pattern be modeled by a linear function? Create a table, graph, create a table and graph to support your answer. Okay, so for a table, in the next slide, it's going to ask us stage number and number of boxes. So for stage 1, I have 6 boxes. For stage 2, I have 6, 7, 8, 9, 10 boxes. For stage 3, I have 1, 2, 3, 4, 5, 6, 7, 8 on the bottom. And then I have 2 rows of 4, so I have 16 boxes. And then for stage 4, I have 9 on the bottom, and then 15 for those 3 rows. So then I have 24 boxes. Okay, so stage number 1, 2, 3, 4, 5, 6, and a number of boxes. Let's go back here. We said we had 6, 10, 16, and 24. 6, 10, 16, and 24. And if we're trying to think about a pattern, if we were to try and think about stage 5, if I were to draw stage 5, I would have 10 boxes on the bottom because this stage had 9. So I'd have 10 boxes on the bottom, and then I'd have 4 rows of 6. So 4 rows of 6 would be 24. So 24 plus 10 would be 34. And then for stage 6, remember we added 1 box to the bottom each time. So I would have 11 boxes on the bottom, and then I would have 5 rows of, if I had 4 rows of 6 here, 4 rows of 6, then I would have 5 rows of 7 here, which would be 35. So then it would be 35 on the top here, right here, and then 11 on the bottom. So that would be 46. Says, is the relation a function based on the table of values? Well, a function, to be a function, every input has to correspond to one unique output. So these are my inputs over here. Oops, I don't know why I keep skipping my N. Inputs right here, and these are my outputs. And if I look, each of these inputs only corresponds to one unique output. So yes, each input has one unique output. And is the relation linear based on the table of values? Well, I'm going to try and find the first difference again, just like we did last time. So I'm just going to write first difference here and try and find the difference between the y values. So in order to get from 6 to 10, I have to add 4. To get from 10 to 16, I have to add 6. To get from 16 to 24, I have to add 8. 24 to 34, I have to add 10. And 34 to 46, I have to add 12. So you might notice there's actually a pattern here. And in high school, you'll actually take the second difference. So you'll find the difference between the first differences because every single time I'm adding 2. Right now, we're just going to know that this is not linear because the difference between the number of boxes is not constant, or the first difference is not constant. So I'm going to say no. The first difference is not constant. Now we're going to graph. So let's go ahead and just graph first. Stage number 1 would have 6 boxes, and this looks like it's going up by 4, 8, 12. Okay, so for if I have 6, it's going to be right here. Stage 2 would have 10. Stage 3 would have 16. 4 would have 24. 5, 34, and 6 would be, oops, oh, I put my 5 on the wrong spot there. Okay, 5 would have 34, and then 6 would have 46. So if I were to draw a line through here, it wouldn't actually be a straight line. I could draw through here, but it would look something like this. It would be a curved line. And when we have a curved line like that, it's actually going to be a quadratic function. So is this relation linear based on the graph? Well, no, because the points do not fall on a line. So the points are not on a straight line, I should say. But is the relation a function based on the graph? So when we are trying to tell if a function is based on a graph, remember we have that vertical line test. So I can draw a vertical line here, just straight up and down. And if I were to move that vertical line anywhere to the left or anywhere to the right, it would still only hit 1 point on that graph. So yes, because of the vertical line test. Okay, last problem here. Owen earns quarters each day that he makes his bed every morning. So, okay, so he earns quarters each day he makes his bed. On the first day, Owen's mom gives him 2 quarters. On the second day, Owen's mom gives him 4 quarters. On the third day, he receives 6 quarters and 8 quarters on the 4th day. Owen makes his bed every day, and this pattern continues. The model shows how many quarters Owen earns each day. Each box represents 1 quarter. Okay, so this is 1 quarter and this is 1 quarter. Consider the relationship between the number of quarters received on any given day and the day number. What is the independent variable and what is the dependent variable? So I always think, what depends on what? Does the day depend on the quarters, or does the quarter depend on the days? And we know that the day number doesn't depend on quarters, so that would be our independent variable is the day number. And the dependent variable would be the number of quarters on a given day. The number of quarters on a given day. Is the data linear? Explain your reasoning. Okay, so to be linear, we know that it has to have a constant difference between basically the dependent variables or the output. So if I'm going to look at, is there a pattern between the outputs? To get from day 1 to day 2, I have 2 here, and I have to add 2 to get to here. So this is my 2 that I'm adding. To get from day 2 to day 3, I just have to add 2 again. To get from day 3 to day 4, again, I just have to add 2. So this would be my first difference between the outputs. So I can say, yes, the number of quarters being added each day is 2. Okay, so now we're going to get into our equation. Define your variables and write an equation to model the relationship between the number of quarters received and the day number. Okay, so for day 1, we know that we had 2 quarters that day. And then our total number of quarters would have been 2. For day 2, we received 4 quarters that day. I'm just going to focus on the first column first. So day 3, we got 6 quarters. Day 4, we got 8 quarters just that day. Day 5, we would have gotten 10 quarters just that day. So the total number of quarters on day 1 was 2. Total number of quarters on day 2, though, I would have had 2 plus 4, so 6. And then the total number of quarters on day 3, I would have already had 6. We're assuming that we're not spending our quarters. So I would have already had 6 quarters, and I should erase that because that kind of looks like a decimal now. I would have already had 6 quarters, and I added 6, so I would have 12. Then I would have already had 12, and I would have added 8 on day 4, so I would have had 20. Day 5, going into day 5, I had 20 quarters, but I also received 10, so I would have had 30. So my variables here, you can use X and Y, or you can use D and Q. So I'll kind of do this both ways. I'm just going to call D is equal to the day number. But we also know that this is our independent variable, so this would also just be X. So our dependent variable would be the total number of quarters. So the number of quarters. Okay, and consider the relationship between the total number of quarters Owen had earned and the day number. Complete the table of values. So, oh, I'm sorry, we forgot to write our equation. Okay, so for our equation, okay, to make our equation a little bit easier, I should have actually defined my dependent variable Q or Y as the number of quarters added that day. So this is my X and this is my Y, okay? And my equation to get from day 1 to day 2, I can add 1 or I can multiply by 2. You're going to see that from day 2, I'm multiplying the day number times 2. So 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. So when you write an equation, it should work for every single example. So this would be Y would be my number of quarters added that day equals 2 times X. Or if you were using D and Q, you could write Q equals 2 times the day number, okay? And we already completed the table of values. We actually went a little bit out of order here. It's asking, and E is the data for the total number of quarters linear. Explain your reasoning. Well, in order to tell if this is linear, the number of quarters being added to the total each day would have to be the same. But this is actually changing. And this question can actually be a little bit confusing because it's referring to something really specific. It's saying, is the data for the total number of quarters linear? So we're not actually looking at this one. We're looking at this column right here to see if that's linear. So the total number of quarters, in order to find the first difference, I know we usually do it on the right, but I'm just going to do it right here for more space. We say, is this constant? To get from here to here, is this constant? So from 2 to 6, I have to add 4. From 6 to 12, I have to add 6. From 12 to 20, I have to add 8. And from 20 to 30, I have to add 10. So that is not constant. We can see there's kind of a pattern there, but it is not a constant first difference. So no. the first difference is not constant. And I can say because the number of quarters, see if I can scroll this up a little bit, there we go, being added to the total each day is changing. We're not adding the same amount to the total every single day. Okay. So other linear versus nonlinear hints. So we should know by now that in order to be linear, our first difference must be the same. And this is the difference between the y values. So I'm just going to make up a table here, 1, 2, 3, 4. And this is my x and this is my y. And if I have 12, 14, 16, 18, you can see that I'm making these numbers because my first difference, I'm doing the same thing every single time. I'm just adding 2 every single time. If we have something that is nonlinear, really, we know it's nonlinear if it doesn't have this constant first difference. But in high school, you will learn something that's quadratic, and you'll actually take the second difference. So if there was an example where something was nonlinear and specifically quadratic, I could have 1, 2, 3, 4, and instead I would have 12, then 14, and then I would have 20, and then 26. So if I were to take the first difference here, it would be +2, then, oops, I actually did this wrong. Okay, so I just changed these numbers here. So if I were to change this to 18 and 24, then I could use this example. So 14 to 18, I would do +4, and then 18 to 24, I would do +6. And you guys have been probably noticing that there's a pattern. So this was my first difference. And we could also take the second difference. So if we take the second difference, to get from 2 to 4, I add +2, and to get from 4 to 6, I also add +2. So if my second difference is the same, this is what we would call quadratic. And that's where we get a nice parabola or something like that. So keep this in mind for when you guys get to high school with functions, that the second difference, if the second difference is the same, it's quadratic, and we will have an equation that has an x squared in it. Okay. So I don't want to get too far into this because this is a whole nother lesson in high school. But the most important thing that you can remember right now is if something is linear, then it is going to have a constant first difference or difference between the y values. Okay, so that is it for the lesson. Please make sure to join office hours if you have questions, or to go ahead and email your teacher.